Hello, everyone. Today, we're going to go over a computational fluid dynamics tutorial in FEBio. The example problem that we are going to analyze is Taylor-Couette flow. My name is Gerard Teschen. I'm professor of mechanical engineering at Columbia University. So Taylor-Couette flow is the flow within this tubular fluid domain, where you have the inner wall and the outer wall can rotate, although in this particular tutorial example, we're only going to allow the inner wall to rotate with a rigid body motion, and the outer wall will be stationary. So what happens is initially the fluid will want to turn around, but as we go faster and faster, this Taylor number, this non-dimensional number, will exceed a certain critical value, and the flow will become three-dimensional, and we will end up having vortices that are produced through the height of the tube. So what I'm going to do is I'm going to demonstrate to you how we can simulate this problem using FEBio. So I'm going to switch to the FEBio software, and I'm going to start a new model. In this new model, I'm going to select a fluid mechanics analysis, and I'm going to click OK. I'm going to create the tubular geometry, but before I do, I'm going to select the units for my problem, and I'm going to modify them to SI units. I'll click OK. I'm going to pick this tubular geometry here, and I'm going to center the tube at the origin. Then I'm going to pick the inner radius to be 0.03 meters. The outer radius is going to be 0.035 meters, and the height is going to be 0.025. These are the dimensions that I picked for this particular example. And then when we zoom in, we can see the geometry of the tube right here. Now that I have the geometry, the next step is to obtain the mesh. So I'm going to set the mesh so that the elements are all hexahedral, 8-node hexahedral elements, roughly all the same size, about 1 millimeter on the side. So since I have 25 millimeter height, I'll pick 25 stacks. The fluid domain along the radial direction is 5 millimeters, and therefore I'm going to put 5 elements. And in the circumferential direction for 1/4 of the tube, I'm going to have 47. When I say apply, you can see that a mesh has been created, and this mesh is nice and regular. However, in fluid mechanics, we're going to develop boundary layers near walls where there's no slip condition. And so what we need to do is we need to create a biased mesh. So I'm going to convert this mesh to an editable mesh. And then what I'm going to do is I'm going to select the faces, multiple faces here on the boundaries, on the outer boundary. So initially the geometry is segmented into 4 domains. So when I do this selection, I have to select 4 surfaces. And then I'm going to create the boundary layer using this tool in the meshing tab. Basically, what I want to do is for this first layer of elements away from the wall, I'm going to have 5 elements instead of 1. So I'm going to say I'm going to have 5 elements. And I'm going to have each element become twice as thick as the previous one. So it's a biased mesh. When I say apply, you will see that it actually created a biased mesh exactly as I wanted it. And then I'm going to do the same thing on the inner wall because that's also a no-slip wall. And when I do that, I have now a biased mesh in both directions. So I'm done creating the mesh. So what I want to do next is I want to assign a material to this mesh. I'm going to turn off the mesh by using the keyboard shortcut, the letter M, and just turn off the display of the mesh. I'm going to go to the material section, and I'm going to say add material. I right-click with the mouse, and I say add material. And because I selected the fluid module, then the only category that's available to me is just a category of fluids. So the material that I want is going to be a fluid. And I want it to be viscous. Of these various options for the viscous response, I'm going to pick a Newtonian fluid. And I'm going to assign the properties of water. FEBio doesn't have built-in properties for any substance, but I can put the name of whatever I want for this particular material. I'll call it water. Then I'm going to assign the properties of water. We'll pick, idealized properties, 1,000 kilogram per cubic meter for the density. The bulk modulus under ambient conditions is 2.2 gigapascal. So I'll say 2.2 e to the 9. And the viscosity of water is 0.001 pascal second. So these are the properties. And since this tubular domain is already selected, all I have to do is click on the plus sign here, and that will assign this material, which has this color, to this domain. Let me save this model before I forget. I'll go to my desktop and I'll take the default name model 1. Now I'm ready to apply boundary conditions. Remember, we decided that we want the outer wall to be stationary. So I'm going to click on the surface selection. I'm going to select this outer surface. So it should be apparent that I selected the outer surface. I'm going to go to the physics menu and I'm going to say add boundary condition, but later I'll use this keyboard shortcut to add boundary conditions. So the default one here is the one that I want, 0 fluid velocity. I'll say okay. But I want to specify that I want 0 fluid velocity in all 3 coordinate directions, x, y, and z. So this completes one of the boundary conditions I want to apply. The other boundary conditions I want is that I don't want flow in the z direction on the top and bottom surfaces. I'm going to keep the flow constrained within this tubular geometry. So I'm going to use the keyboard shortcut for boundary conditions. Once again, 0 fluid velocity, but this time I'm only going to click on the degree of freedom for the z component of the fluid velocity. So I now have this boundary condition. And finally, I want to specify a rotational velocity on the inner wall. So in FEBio, this actually becomes a surface load. So under surface load, I will select the fluid rotational velocity right here, and I'll say okay. The options that I have is to specify the angular speed. So I'm going to ramp up the angular speed, but up to a value of 1.5 radians per second. By default, the rotation is about the z-axis, 0, 0, 1, so I'll keep that. And by default, the axis passes through the origin, which is fine since I placed the tube at the origin. So now we're done with this boundary condition. So basically, we're done applying the boundary conditions here, except that one thing I told you a moment ago is that I actually want to ramp the velocity, the angular speed, up. Remember, fluid dynamics problems are problems in dynamics. Therefore, we don't want sudden accelerations and decelerations. So what I'm going to do is I'm going to click on the curve editor here, expand the load section, and I see here the fluid rotational velocity. I'm going to select the angular speed. By default, FEBio will make the angular speed ramp up. This curve is a scale factor. So it ramps up from 0 at time 0 to 1 at time 1. So I would like this curve to be smooth instead of having this sharp transition, because that would imply a sudden deceleration as I have a sharp corner. So instead of using a line, I'm going to use control points. And I'm going to use a cubic spline with control points. So I'm going to add a control point here at roughly halfway at 0.499 second. And I'll make sure that this control point is at 0. And then another control point at 0.501 seconds. And I'll make sure that this is equal to 1. When I do this, then you can see that I have a nice sigmoidal rise. And then after time 1, the angular speed will remain constant. So now I've completed the application of all the boundary conditions, including the time response that I want. So now I need to select the solver, which in our case is obviously going to be the CFD solver. So I go to physics, add analysis step, and the only solver that's available to me because of the initial selection that I made when I launched FEBio Studio was fluid mechanics. So I come. I need to decide how long I want my analysis to run. So the default time step size is 0.1 second. I'm going to keep that default value. It actually works for this problem, but I'm going to pick 400 time steps. So in the end, I'm going to have an analysis that runs up to 40 seconds. I'm not going to allow the step size to go above 0.1 because otherwise the solution will not converge well. But if the iterative solver struggles at a particular time step, I'm going to allow it to take shorter time steps. The minimum step size here of 0.01 seconds is probably okay, but just to be on the safe side, I'm going to make it even smaller. What I'm going to do is I'm going to say, however, when you cut down the time increment from one step to the other, let's do it aggressively. So let's cut down the time increment by a factor of 2. That's what aggressive does. So then how does FEBio determine, whether to cut down a time increment at the next time step? It decides whether the number of iterations that it took to solve the previous time step exceeded this optimal iterations. I'm going to pick this number to be 50 instead of the default of 10. These are the parameters for the nonlinear solver. I won't go into all the details, but what we're going to do is we're going to use a quasi-Newton solver, which actually requires us to set the residual tolerance to non-zero. So I'll set it to 0.001. This quasi-Newton method for non-symmetric stiffness matrices is the Broyden method. That's the one that I want to use. I'm going to allow no more than 5 full Newton reformations of the stiffness matrix, because that will be the most time-consuming part during the analysis time. But I will allow up to 50 quasi-Newton updates. So in total, it'll do 5 times 50, which is up to 250 iterations at any given time step before it decides that it's going to fit. Now, it can also fail, of course, if it encounters other problems along the way. One of the issues is that the residual of the solver keeps growing, and it keeps growing. You don't want to run 250 iterations to watch it grow to 10 to the 20. So I'll reduce this maximum residual to 10 to 10, essentially. And this is really by trial and error. So I'm telling you parameters that I selected based on running this problem before. And then I'm not going to reform the stiffness matrix when there's a divergence during an iteration. I would prefer to restart at the shorter time step. And I'm not going to reform the stiffness matrix at each time step, because that would be too time consuming. So I'm going to uncheck these 2 boxes. And then I'm going to save. Now, normally, I would also tell you, now let's check what output variables we want to save in the plot file. But for the fluid solver, the default output variables that are included are very comprehensive, so we don't need to add any additional ones. The only time is if you're concerned that the plot file is going to be very large, you might in fact decide not to save as many as we have here. For now, I'm going to save this file and I'm ready to run it. So all I have to do is say febio run, febio, and take the default settings, which come when you install febio Studio on your computer. When I say run, you're going to be able to watch the iterations down here. What you're going to see is that the number of equations that is solving is about 250,000, which is, a reasonably small number that febio will do a good job with. And so now what you're saying is that the initial reformation of the stiffness matrix and its factorization was time consuming, but since we're doing quasi-Newton updates for up to 50 iterations, subsequent time increments are proceeding nice and smooth. In principle, you can actually watch the solution while it's running. Now, this analysis will actually take about 45 minutes to run on a reasonably, fast desktop computer. It could actually run faster on your computer, maybe a little bit slower. I'll click on this plot file, folder here and open it up. So we can actually take a look at the plot file while it's running. So we will have to reload the plot file as the solution progresses. So I just want to give you a preview that I can take a look, for example, at the fluid velocity magnitude. And at time 0, it's 0 everywhere. But as I advance in time, it'll increase at the inner wall, because that's where I'm prescribing the rotational velocity. And of course, as time progresses, it'll spread further and further away from the inner wall. In fact, the solution, when I loaded this file, had already reached time 1 when the angular velocity has reached its maximum value. What I'm going to do now is I'm going to switch to the actual plot file that I generated before. And, because this solution here, we're already at time 3 seconds, it's not too bad. We want to go to time 40 seconds, remember, but it'll struggle a little bit more once the laminar flow breaks apart and we start having vortices. So what I'm going to do is I'm going to go back to the model. For now, I'm going to stop this particular model. And what I'm going to do is I'm going to close it. And what I'm going to do is I'm going to open the file that I already solved, which is on my desktop, and it's located in this folder, TaylorCouette flow. When I open it, this file is about 3 gigabytes. And so it takes a little bit of time, a few seconds to load it, but it's entirely reasonable amount of time given the size of the file. Once the file has loaded, I can now see that the time actually went all the way to 40 seconds, you can see here. By the way, before I start showing you the results, I want you to know that this model that we just created together, if you don't want to recreate it yourself, or if you find that you're not able to reproduce the exact same results, you can go to the repository tab down here, click on Connect, and then you can see here the repository for the febio Studio project. under the tutorial folder, you can scroll down, you'll find the Taylor-Couette flow. This is the file that I created. You can see it's got the same name, and I uploaded it here. So you should be able to download this file by double-clicking on it. When you double-click on it, it'll put it in a folder on your local computer at a specific location. It'll prompt you for it. Anyway, so now that we took a look at that, let's focus on the results for this particular problem. Once again, let me turn off the mesh. And what I'm going to do now is I'm going to look at a top view. I'm sorry, front view, given the orientation of the part. And I can, for example, look at the fluid velocity, magnitude. Now I can play the animation so you can see that the velocity increases a little bit over time. And here the color bars are updated dynamically. So the minimum value is 0. The maximum value has now reached the maximum because we exceeded time 1 second when the angular velocity reached its peak of 1.5 radians per second. And what you see at first is everything looks fine. But what if we turn around and we say, look, I would like to take a look. I'll go back now to my perspective view. And I'm going to take a section through my model. And what I'm going to notice is that already the fluid magnitude is starting to fluctuate. Let me turn off, not show the section plane. Let me go back a little bit in time. This is when the flow was nice and regular. And then as time progressed, you can see this is just the fluid velocity magnitude, but it's starting to fluctuate. So this velocity fluctuation is what we, eventually leads to the production of these Taylor vortices. This is why this problem is famous and is named after Taylor and Couette. So you can see that the magnitude of the velocity is no longer uniform along the z direction. What I'm going to do is I'm going to go to my preferences and I'm going to change the lighting direction so it comes from the left instead of from the right. And if I say apply, then you will see less of a shadow on this side. So now what we're going to do is we're going to look at different ways that we can display these same results. Remember that these are vortices which are forming. So these vortices are forming because the fluid velocity in the vertical direction is no longer 0. So initially, the fluid velocity in the vertical direction is negligibly small. So even though you see some color variations here, keep in mind this is on the order of -7 meters per second. But as time progresses and the scale bar, again, dynamically adjusts itself, it doesn't have to, you can make it static, but you're going to see that the velocity in the vertical and the z direction will no longer be 0. Now it's risen to values that are approaching the value of this velocity magnitude within the field. There are fluctuations. The flow is not reaching steady state yet, but eventually over time you will see that these velocities will stabilize and it'll come to a quasi steady state. If we run the analysis for even longer than 40 seconds, we might find that it's going to start going unstable again for a period of time. It's that's the nature of fluid flow at these relatively elevated values of the Taylor number. So this here is the magnitude of the velocity, not the magnitude, it's the component of the velocity in the z direction, but I can also look at the vorticity. So the vorticity magnitude, you can see here the vorticity, because after all, the whole idea is that we're creating vortices. Once again, let me scroll back and let's watch and take a look at the magnitude of the vorticity. Initially, it's nice and uniform, but once again, it breaks apart. And you can see that it starts going around, and it's not an axisymmetric problem. For a period of time, this axisymmetry breaks down. And so what we can see is that these vortices evolve in this map. It would be nice to show contours also in the part of the section that was cut away. So the way that we do this is, for example, I can actually select here the isosurface plot. And for the isosurface plot, I can select, once again, the fluid velocity, vorticity magnitude. But then I'm going to say allow clipping, no, meaning allow me, you should show me the part of these sheets that occurs outside this domain. Let's scroll back to the beginning and let's play now this animation. The other thing we're going to do is, because we're going to have 5 slices, let's make them semi-transparent so we can look through them. And let's also make the domain of the fluid semi-transparent. So I'm going to click on the material here and make the fluid domain semi-transparent. Now you can see that the vortices are uniform. They form, isosurface of constant vorticity are cylindrical and concentric. However, over time, as we approach time 10 or 11, we're going to see these will start to break apart. So there are 5 isosurfaces, and these are the values that it decided to dynamically adjust between the minimum and the maximum to get us these 5 sheets. Now you can see that after time 11, it started breaking apart. You can see how these isosurfaces are actually illustrating to us the formation of these vortices. So this is a nice way to visualize the flow. There are other flow visualization features. I'm not going to demonstrate all of them here, but there will be additional tutorials that we will post over time on fluid mechanics problems, and you'll be able to see other features as well. So I can make this animation go a little bit faster. And for example, I can request 100 frames per second, but honestly, this will be also limited on the graphics capabilities of your computer and how powerful your computer is. So now we're going to reach time 40. And what you're going to see is over time, at least for up to 40 seconds, the flow is becoming, I'm going to say, quasi-steady. It's not clear to me that it'll remain steady forever, but it'll become steady by roughly time 40. So you can actually view it in multiple orientations in this map. Okay, so this brings us to the end of this presentation on how to create the geometry, the mesh, assign material properties, assign boundary conditions, pick the properties of the solver for this particular problem, which is a Taylor-Couette problem. So what I'm going to do now is I'm going to quickly summarize what we did in case you didn't have time to write things down. So for the geometry, I picked the inner radius to be 0.03 meters, the outer radius is 0.035, and the height is 0.025. For the mesh, the slices, we had 47, the segments, we had 5, the stacks, we had 25. Then we added boundary layers on the inner and outer walls, and we used a bias of 2 and 5 segments. And for the material properties, we called the material water, and we assigned the properties of water at standard atmospheric conditions. Okay. The other things that we did was to apply the boundary conditions. So we fixed the velocity along X, Y, and Z for the outer wall. For the inner wall, we prescribed a rotational velocity about Z of 1.5 radians per second, and we increased it sigmoidally using the curve editor with control points shown here to go from 0 at time 0 to 1 at time. And we also applied zero velocity along the Z direction for the top and bottom. These are the solver settings. I'm flashing them up on this slide because when you replay this recording, you can actually, pause and copy things if you didn't see them or you felt like they went by too quickly during the actual demonstration. Finally, the Taylor number for this particular set of properties, if we plug in omega is 1.5 radians per second, R1 is 0.03 meters, R2 is 0.035, and the kinematic viscosity is the ratio of the dynamic viscosity and the mass density, we find that the Taylor number for this problem is about 8,400, and the critical value according to the literature for instability is about 1,700. So we're clearly in the range of instability. The vortices start forming approximately at time 12 seconds, maybe around 11 or 12 seconds. And we seemingly reach steady state at the final analysis time. So this is a summary of what we did for this particular problem. Now, if you find that febio is an interesting software that you want to try, then you can download it for free, obviously, from febio.org. We have executables for Windows, Mac, and Linux. You can also find the source code on GitHub if you want to compile it yourself. We have a forum where you can ask questions, any questions. The people who will answer them are the developers. I will show you who they are in a moment. And if you become an advanced user and you develop your own plugins where you add features to the code using documentation that we provide and with answers that we can give you on the forum on how to do that, then you can share your plugins on the febio.org website. This project is supported by the US National Institutes of Health. So all this funding allows us to do this work and then provide the software to you at no cost. These are the team members: Professor Weiss at the University of Utah, myself at Columbia University, Steve Moss, Ben Ellis, and Michael Heron, all at the University of Utah. This is the current team that's developing FEBio and FEBio Studio. If you're interested in understanding the CFD equations that we are solving, you can spend a few more moments watching this video. Basically, in FEBio, the approach that we follow is not the conventional approach in computational fluid dynamics. Most commercial solvers use the finite volume method. We use the finite element method. Most commercial solvers will use stabilization methods to facilitate the solution process, whereas in FEBio, we don't use these types of stabilization methods, but in exchange, you must use biased meshes wherever you have no slit boundary conditions. So we solve the momentum balance equation, which is the mass density times the acceleration is equal to the divergence of the stress plus the mass density times the specific body force, such as gravity, for example. The stress is a contribution from the pressure and from the viscous part of the stress. And we solve the mass balance equation, not by assuming incompressibility. We don't say that the divergence of the velocity is zero. Instead, we assume that the fluid is slightly compressible. So this is the mass balance equation, but we actually use this kinematic constraint, which is well known in some fields of continuum mechanics, less well known in fluid mechanics. But this kinematic constraint is between the volume ratio J. So the J dot here is the material time derivative of J is equal to J times the divergence of the velocity. If the volume ratio remains equal to 1 and is constant, then the fluid is incompressible, in which case J dot is 0 and the divergence of the velocity is 0. But we don't make that assumption. We actually solve for J. So what we do is, if you substitute this expression into here, you can actually rewrite the mass balance equation as this very simple ordinary differential equation, which can be integrated, concluding that rho times J is a constant. We call that constant the referential mass density, rho r. So that would be the mass density when J is equal to 1. So FEBio then solves the momentum balance here, and it solves this, kinematic constraint equation. And the two unknowns that it solves for are J and the velocity V. But we calculate the pressure using an equation of state that relates the pressure to 1 minus J, which is the negative of the dilatation, the relative volume change. And that's where we need to introduce the bulk modulus of the fluid. So for a fluid like water, the bulk modulus is very high. So we approximate incompressible flow, but we don't make that assumption from the outset. There's no idealization. And we can propose equations of state for the viscous stress. You saw in the demonstration that I gave you a number of non-Newtonian fluid viscous stress models. But if we pick a Newtonian fluid, we have the usual shear viscosity mu that relates the rate of deformation tensor to the viscous shear stress. So that is the underlying approach that FEBio uses. If you're interested, you can find the details of this approach in this paper that we published. Again, I'm just going to flash it up here. And when we published the paper, we ran a lot of verification and validation problems. These problems are available in the FEBio Studio repository under user projects. You will see it under the heading called FEBio CFD paper, published in the Journal of Biomechanical Engineering in 2018. These are all the problems that were presented in that paper, and you can download them and run them yourselves. Very good. Thank you for watching this presentation, and I hope to follow up with additional tutorials in the future. Take care. Bye-bye.